how they create simple linear regression as well. So this video is going to be on multiple linear regression, and it is different from simple linear regression, where a simple linear regression has one independent variable, usually x, and one dependent variable, usually y. Well, multiple linear regression is you have more than one independent variable, being x1 or x2 or x3, and only one dependent variable, being y. So what we're going to do is we're going to go over some sample programs on multiple linear regression, and I think this is going to be a long video. So the first thing we're going to do is we're going to simulate a multiple linear regression program, and the first thing we're going to do is we're going to set our seed. And the reason why you set your seed is so every time you run the program, the variables will be initialized to the same value. So we type set.seed brackets 1, 2, 3, and you can put any number you want within the brackets. And then we're going to simulate our predictors. So advertising is going to be our norm. That's a randomly sampled normal distribution with 60 samples, a mean of 20, and a standard deviation of 5. And the staff is going to be our norm with 60 samples, a mean of 10, and a standard deviation of 2. And now we're going to calculate the outcome variable with true coefficients. So that's the advertising and staff is going to be x1 and x2, and sales is going to be y. So sales is 4 plus 2.5 times advertising plus 3 times staff plus our norm, 60 samples with a standard deviation of 10. And then we're going to take the two independent variables and the dependent variable, and we're going to create a data frame out of that. So data becomes data.frame bracket sales, comma, advertising, comma, staff. And so sales is your y variable, and advertising and staff are going to be your x1 and x2 variables. So we're going to fit the multiple regression model. So model becomes LM. LM stands for linear model. Bracket sales is your y variable. And you've got your tilde, advertising plus staff, comma, data equals data. And then we're going to summarize the model. So this is your summary of your model. Your formula is going to be LM, that's linear model, brackets formula equals sales, tilde, advertising plus staff, comma, data equals data. And then you've got your residuals being minimum, the first quartile, the median, which is also the second quartile, the third quartile, and maximum, which would be the fourth quartile. And then you've got your coefficients being your intercept, your advertising, and your staff. So your intercept gives you a p-value of 0.94046. Advertising has a very low p-value, and staff has 0.00252. And then you've got your significant, and then you also got your residual. Standard error is 10.47 on 57 degrees of freedom. So you remember you had 60 samples, and then 60 minus 3 is 57. And then you've got your multiple, R squared is 0.6724. Your adjusted R squared is 0.6609. You've got your F statistic, which means that this model was based on an F distribution. So your F statistic is 58.5 on 2 and 57 degrees of freedom. and your p-value is also a very low value. So now we're going to plot the predictor, the relationships, and the residuals. So you've got par brackets m fro equals c, which is going to be a vector 1, 3. So you're going to have 3 plots side by side. And then so 1, we're going to have sales versus advertising. So we're going to plot brackets, advertising, comma, sales, PCH, that's the size of the dot, equals 19. Color equals steel blue. Main is your title. Is sales versus advertising. XLab, that's the label on the x-axis, is advertising. And YLab, which is the label on the y-axis, is sales. And just 1 second, I have to wipe my glasses. I can't see very well without my glasses, and I can't see very well in my glasses. So now we're going to create a line. So you've got AB line brackets LM. So that's linear model brackets sales tilde advertising. The color is red and the line width is 2. And then what we're going to do is we're going to plot the sales versus staff. So plot bracket staff, comma sales, comma PCH equals 19, color equals dark green, main, which is your title, is sales versus staff, XLab is the label on the x-axis, is staff, and YLab, which is the label on the y-axis, is sales. You're going to put another line in there, AB line, brackets LM, brackets sales tilde staff, and color equals red and line width equals 2. And now what we're going to do is we're going to plot the residual plot. So plot brackets model $ fitted dot values, comma model $ residuals, comma PCH equals 19, color equals purple, main, which is your title, is residuals versus fitted. XLab is the label on the x-axis, is fitted values. YLab is which is the label on the y-axis, is residuals. You're going to put another line in the plot, AB line brackets H, which means it's horizontal, equals 0. Color equals red, line width equals 2, and par brackets M pro equals C, 1 brackets 1, 1. So that's another vector that you're creating, and it says reset the layout. So this is the plot that we have created. So we have created 3 plots on 1 row. The first plot is sales versus advertising. The second plot is sales versus staff. And the third plot is residual versus fitted. So sales versus advertising has a pretty high coefficient, and the sales versus staff has a not so high coefficient, and your residual just shows you what your residuals are. So now what we're going to do is we're going to talk about multicollinearity. And so multicollinearity happens when predictors move together so strongly that the regression model cannot tell which one is actually driving the outcome. So we're going to give you a little program to demonstrate that. So we're going to simulate multicollinearity in this example. So the first thing that you want to do is you want to set your seed. So every time you run the program, the variables are going to be initialized to the same value. So you type set.seed brackets 1, 2, 3, but you can put any number you want within the brackets. N becomes 200. And so that's going to be your number of samples. And we're going to have two predictors that are highly correlated. So X1 becomes R norm. That's a randomly sampled normal distribution with N or 200 samples, a mean of 50, and a standard deviation of 10. And then X2 becomes X1 plus 0.9 plus R norm. That's a randomly sampled normal distribution of 200 samples with a standard deviation of 2. And then so X2 is almost a copy of X1. And then we're going to calculate the outcome variable, which is your dependent variable. So Y becomes 3 plus 0.5 times X1 plus 0.5 times X2 plus R norm. That's a randomly sampled normal distribution, brackets N, which is 200 samples with a standard deviation of 5. We're going to fit a multiple regression. So model becomes LM, that stands for linear model, brackets Y tilde X1 plus X2. And then we're going to print off a summary of the model. So this is a summary of the model. So the formula is LM brackets, formula equals Y tilde X1 plus X2. And then we've got the residuals. So you've got the minimum, the first quartile, the median, which is also the second quartile, the median, the third quartile, and the max. Then you've got your coefficients for the intercept X1 and X2. And then you've got your significant codes. You've got your residual standard error is 4.84 on 197 degrees of freedom. So that is 200 samples minus 3. Multiple R squared is 0.7703. Adjusted R squared is 0.768. Then your F statistic is 330.3 on 2 and 197 degrees of freedom. And your p-value is a really low value. So now after we summarize the model, we're going to visualize the multicollinarity. So we're going to create a scatter plot showing the correlation between X1 and X2. So plot brackets X1, comma X2, and then main, which is your title, is a strong correlation between predictors, which is multicollinarity. And XLab is the able on the x-axis being X1. YLab is the label on the y-axis being X2. And PCH is the size of the dot is 19. Color is RGB, and that's like a type of something to do with computers. And then brackets 0, 0, 1, 0.5. And so that's a vector that you have created that has several colors on it. We're going to put a line in there in the plot. It's bracket AB line, brackets LM, that's linear model, brackets X2 tilde X1, color is red, and line width is 2. So we're going to come over here and we're going to look at the plot that has been created. So this is the first plot that has been created. So this is a strong correlation between predictors. So you can see that the regression line, the predictors on the regression line are sitting right on the regression line. So it has a strong correlation between the predictors. Okay, now what we're going to do is we're going to take the regression, coefficient, instability, and so we're going to fit a simple regressions. So that's M1 becomes LM, that's linear model, brackets Y tilde X1. M2 becomes linear model, brackets Y tilde X2. And we're going to extract the coefficients. So coef values equals C, that's the vector you're creating, brackets M1 equals coef M1, 2, and M2 equals coef M2, 2. Both X1 equals coef model 2, and both X2 equals coef model 3. And then we're going to create a bar plot to show instability. So bar plot, brackets, coef values, comma, main as your title, coefficient instability caused by multicollinearity. Y lab is the label on your y-axis, is coefficient value. Your color is going to be a vector being sky blue, tomato, and tomato. And then we're going to come down here. We're going to look at the bar plot that has been created, and this is coefficient instability caused by multicollinearity. So you've got M1X1 is blue, M2X2 is blue, and both X1X1 is tomato, and both X2X2 is tomato. So that's an example of coefficient instability caused by multicollinearity. So the next thing we're going to do is we're going to talk about an interaction term and test whether the relationship between a predictor X1 and the outcome Y changes depending on the value of another predictor X2. And so we're going to write a program. We're going to go over the program to demonstrate that. So we're going to simulate data with an interaction effect. So the first thing we want to do is we want to set our seed. And so every time you set your seed, every time you run the program, when you set your seed, the variables are going to be set up to the same values. So you have set.seed brackets 1, 2, 3, and then you can put any number you want in your brackets. And then N becomes 200, that's the number of samples. X1 becomes R norm, which is a randomly sampled normal distribution of 200 samples with a mean of 10 and a standard deviation of 2, and that is predictor number 1. And then X2 becomes R norm, that's a randomly sampled normal distribution of 200 samples with a mean of 5 and a standard deviation of 1. So that is predictor number 2. So we're going to have a true model, which includes an interaction. So Y becomes 3 plus 0.6 times X1 plus 1.2 times X2 plus 0.5 times X1 times X2 plus R norm with a 200 samples and a standard deviation of 2. We're going to fit the regression model with the interaction. So model becomes LM, that's linear model, brackets Y tilde X1 plus X2. And so this is the same as Y tilde X1 plus X2 plus X1 2X2. And then we're going to summarize the model. So when you summarize your model, you'll call your formula, which is LM brackets formula equals Y tilde X1 plus X2. You have your residuals of min, Q1, median, Q3, and maximum. You have your coefficients with your intercept, your x1, your x2, and your x1 to x2. And the p-values look pretty good, except for x1 to x2, which is really low. You have your significant codes, and then you have your residual standard error is 2.911 on 196 degrees of freedom. You have multiple R squared is 0.8943. Adjusted R squared is 0.8927. You've got your F statistic is 553 on 3 and 196 degree of freedom. And you've got your p-value, which is a really low value. And then we've also got some warnings. So now what we're going to do is we're going to plot the interaction effect. So we're going to pick a representative levels of x2. So x2 levels becomes quantile, brackets x2, comma, and then we're going to create a vector of 0.1, 0.5, and 0.9. Colors is another vector of blue, black, and red. And we're going to create a scatter plot of that. So plot brackets x1, comma, y, comma, pch, that's the size of the dot. Color is a vector of 0, 0, 0, 0.3, I believe. I can't see my screen very well. Main equals interaction between x1 and x2. And xlab, that's your label on your x-axis, is x1. And ylab, that's the label on your x-axis, is predicted y. So we're going to add a regression line for each x2 level. So for I in 1 to 3. And so basically what we're creating is a for loop. You're going to put a curve in there. So curve brackets, predict brackets, model, comma, data dot frame, brackets, x1 equals x, x2 equals x2 levels I. And then so basically what's going to happen is the for loop is going to iterate 3 times because it says for I in 1 to 3. And then add equals true, color equals colors I. And then so your color is going to be either blue, black, or red, depending upon the value of I. And line width is 2. We're going to put a legend in there. So legend brackets, top left, comma, legend equals C, which is another vector, low x2, median x2, high x2. Color equals colors, calls, and your calls equals blue, black, or red, and your line width is 2. So we're going to print that off, and this is the chart that we've created, and it's an interaction between x1 and x2. So the blue is a low x2, the looks like a gray is a median x2, and the red is a high x2. So that tells you the interaction between x1 and x2. So now what we're going to do is we're going to discuss model selection. Model selection in multiple regression is all about choosing which predictors to keep so that the model is interpretable, not overfitted, not missing important variables, and statistically defensible. The major approaches to model selection for multiple regression in R are 1, information criteria, that's AIC, BIC. 2, stepwise selection, being forward, backward, or both. 3, all subsets regression, best subset selection. And for a theory-driven selection, which is forgotten but often the most important. So what we're going to do is we're going to select a model using theory-driven selection because it's forgotten but often the most important. So we've got a program here that we've created to do this. So first thing we're going to do is we're going to set our seed. So every time you run the cell or run the program, the variables are going to be initialized to the same value. So we're going to type set.seed brackets 1. You can put any number you want in there, and we're going to simulate the data. So n becomes 150, which is the number of samples. So x1 becomes our norm. That's a randomly sampled normal distribution with 150 samples. X2 is our norm, brackets n. X3 is our norm, brackets n. X4 is our norm, brackets n. So y becomes 3 plus 2 times x1 plus 0.5 times x2 minus 1.5 times x3 plus our norm, which is a randomly sampled normal distribution of 150 samples with a standard deviation of 1.5. So we're going to take this y, x1, x2, x3, x4, we're going to convert it to a data frame. So data becomes data.frame brackets y, x1, x2, x3, and x4. And then so we're going to create the full model. So full becomes LM, that's linear model, brackets y tilde dot, comma x equals, comma data equals data. And we're going to stepwise the AIC model selection. AIC is like a goodness of fit test. And it stands for something, but I don't recall right off the top of my head what it stands for, but it is the goodness of fit test. So selection becomes step, brackets full, comma, direction equals both, and then we're going to print a summary of the selected. So we're going to start our AIC equals 160.38, and then y tilde x1 plus x2 plus x3 plus x4. So you've got x4, x2, x3, x1. You've got your degree of freedom. You've got your sum of squares. You've got your RSS, and then you've got your AIC. So step AIC equals 158.55. So that's y becomes x1 plus x2 plus x3. And then you've got your x4, x2, x3, x4, x2, x3, x1. So you've got your 1 degree of freedom. You've got your sum of squares. You've got your RSS, and you've got your AIC. And then we have another call being linear model brackets formula equals y tilde x1 plus x2 plus x3, data equals data, and then you've got your residuals, you've got your minimum, you've got your first quartile, you've got your median, you've got your third quartile, and you've got max, you've got your coefficients of x1, x2, and x3, you've got your significant codes. So your residual standard error, that's your RSS, is 1.674 on 146 degrees of freedom. You've got your multiple R squared is 0.6893. Your adjusted R squared is 0.683. Your F statistic is 108 on 3 and 146 DF. And your p-value is a very low value. Now we're going to talk about how the ANOVA fits in with multiple linear regression. So the analysis of variance ANOVA function compares two or more regression models by looking at how much extra variance the meager model explains, whether that extra variance is enough to justify extra predictors, and the ANOVA is performed using a F-test and requires nested models. So we're going to give you a sample program to show you how the ANOVA fits in with model comparison. So the first thing we're going to do is set our seed. So every time we run the program, the variables will initialize to the same value. So you type set.seed brackets 1, and you can type any number you want within the brackets. We're going to simulate the data. So n equals 150, and that's going to be your number of samples. So you've got x1 equals R norm. That is a randomly sampled normal distribution of 150 samples. x2 becomes R norm brackets n, which is 150 samples. And x3 becomes R norm brackets n with 150 samples. So y becomes 3 plus 2 times x1 plus 0.5 times x2 plus R norm brackets n, that's 150 samples, and standard deviation of 1.5. So we're going to create a data frame with our dependent and our independent variables. Y is your dependent variable, and x1, x2, x3 are your independent variables. And so data becomes data.frame brackets y, x1, x2, x3. And then we're going to take two nested models. So you're going to say the model small becomes LM brackets y tilde x1 plus x2, data equals data. And then the model big equals LM, that's linear model, brackets y tilde x1 plus x2 plus x3, data equals data. So you can see that the small model doesn't include the x3. And then we're going to compare these two models using the ANOVA. So you say ANOVA brackets model small, comma, model big. So you're going to compare the small model against the big model. So what it's going to do, it's going to create a data frame. And so you've got your residual degrees of freedom for 1 and 2. And so your I'm going to say that the small model is 1 and the big model is 2. You got your RSS, that's your residual standard error. And then it gives you your residual standard error. You've got your degree of freedom. You've got your sum of squares. You've got your F statistic. And you've got your p-value. And your p-value is 0.81379. So what we've done is we've compared the small model against the big model. So now what we want to do is we want to extract model components from a multiple regression model. We're going to simulate a multiple regression model to show that. And first thing that we're going to do is we're going to set our seed. So every time you run the program, the variables are going to be set up to the same values. So you type set.seed brackets 1, 2, 3, and so you can put any number you want within the brackets. So we're going to define our sample size as n becomes 150, and we're going to define our predictors. So x1 becomes R norm, that's a randomly sampled normal distribution of 150 samples with a mean of 10 and a standard deviation of 2. x2 becomes a randomly sampled normal distribution being R norm with 150 samples with a mean of 5 and a standard deviation of 1.5. you've got x.3 becomes R norm with a mean, with 150 samples with a mean of 0 and a standard deviation of 1. And then so we're going to define our true underlying model. Your true underlying model is y equals 3 plus 1.5 times x1 minus 0.8 times x2 plus 2.0 times x3 plus your error. And then so y becomes 3 plus 1.5 times x1 minus 0.8 times x2 plus 2.0 times x3 plus R norm, that's a randomly sampled normal distribution, brackets n, that's 150 samples, and a standard deviation of 3. So we're going to combine all this data into a data frame. And so the data frame is going to be comprised of y, which is your dependent variable, and x1, x2, x3, which are your independent variables. So my data becomes data.frame, brackets y, x1, x2, x3. So we're going to fit the model. So model becomes LM, that's linear model, brackets y tilde x1 plus x2 plus x3, and data equals my data. And then we're going to create an example model to work with. So model becomes LM, that's linear model, brackets y tilde x1 plus x2 plus x3, and data equals my data, and the summary. And then we're going to summarize this model. So the formula is going to be LM, that's linear model, brackets formula equals y tilde x1 plus x2 plus x3, and data equals my data. So your residuals are going to be your minimum, your first quartile, your median, your third quartile, and your maximum. And then you've got your coefficients for x1, x2, and x3. Then you've got your significant codes. You've got a residual standard error is 2.6 on 146 degrees of freedom. You've got your multiple R squared is 0.6132. You've got your adjusted R squared means 0.6053. You've got your F statistic is 77.17 on 3 and 146 degrees of freedom. And your p-value is a very low value. So now we have what we're doing in this one is we are extracting model components. So now we're going to go through and extract the model components from the data frame that we have just created. So the estimated regression coefficients is COEF model, and then you've got your corporate and you've got your regression coefficients there. Your confidence intervals equals conf int model, and then it gives you a data frame or a matrix with your confidence intervals for x1, x2, and x3. You've got your predicted values, which is fitted model, and it gives you all of your predicted values, and I think we've got 150 samples. You've got your residuals, which is residuals model, which I think it's 150 sample residuals. You've got your standardized residuals, which is R standard brackets model, and I think it's 150 of those as well. You've got your studentized residuals, so R student model, and you've got 150 values for there because you've got 150 samples. You've got your R squared is summary model, $R squared is 0.613. You've got your adjusted R squared is summary brackets model, ADJ R squared is 0.605. You've got your coefficient table, which is the summary of model $ coefficients. So you've got your coefficient table of the data frame. You've got your residual standard error, which is summary model $sigma as 2.86. You've got your F statistic, which is summary model $F statistic, and it gives you your F statistic value of 77.167. You've got your ANOVA, that's your analysis of variance. So it gives you a data frame of how the X1, X2, X3 compare to each other, and also the residuals. You've got your model structure. So you type formula model, and your model structure is Y tilde X1, X2 plus X3. You've got your structure of predictors. So you've got terms model, and then it gives you your structure of predictors. You've got your model frame, model.frame brackets model, and so you get your data frame of 150 rows of data, which is your 150 samples. You've got your hat values, that's your Libridge. So model.frame model. So you've got 150 as well, since you had 150 samples. You've got your Cook's distance, Cook-Stokes distance model, and you've got your answer. You've got your influence measures, influence.measures model, and then that gives you that information. You got your names of components. So that's going to be names brackets model. And so the components are coefficients, residuals, effects, ranks, fitted values, assign, QR, DF residual, X levels, call, terms, and models. And so now what we're going to talk about is nested models. Nested models in multiple regression are where the simpler model is a special case of the more complex model. A nested model is fully contained inside another model. In essence, if the researcher can write a smaller model's formula inside a larger one, the two models are nested. So you've got an example of model A is nested in model B if model B contains all the predictors in model A, model B has additional predictors, and no transformations or structural changes break this containment. So we're going to give you an example of nested models so you can see how they work. So we're going to simulate a multiple regression model. So the first thing you want to do is set your seed. So every time you run the program, the variables are going to be initialized to the same values. So you type set.seed brackets 1, 2, 3, and you can put any number you want in there. So our sample size is n becomes 150, so that means you're going to have 150 samples. And then you've got x1 becomes r norm, which is a randomly sampled normal distribution, brackets 150 samples with a mean of 10 and a standard deviation of 2. X2 is the same thing, but it has a mean of 5 and a standard deviation of 1.5. And X3 is the same thing, except it has a mean of 0 and a standard deviation of 1. So we're going to have our true underlying formula is y equals 3 plus 1.5 times x1 minus 0.8 times x2 plus 2.0 times x3 plus error. So our true model is y becomes 3 plus 1.5 times x1 minus 0.8 times x2 plus 2.0 times x3 plus R norm, which is a normally sampled normal distribution of 150 samples with a standard deviation of 3. We're going to combine y, x1, x2, x3 into a data frame. So it's my data becomes data.frame brackets y, x1, x2, x3. We're going to fit the model. Model becomes LM, that is a linear model, brackets y tilde x1 plus x2 plus x3, and data equals my data. And then so we're going to have an example model to work with. So model becomes LM, that's linear model, brackets y tilde x1 plus x2 plus x3, and data equals my data. And we're going to summarize the model. And so this is the summary of the model, which is the same as what we did just a few minutes ago because I was using the same my data that I did before. So linear model, the formula is linear model brackets formula equals y tilde x1 plus x2 plus x3 and data equals my data. Then you've got two residuals being minimum, first quartile, medium, third quartile, and mix. You've got your coefficients for the intercept x1, x2, x3. You've got your significant codes. You've got residual standard error is 2.86 on 146 degrees of freedom. You've got multiple R squared is 0.6132. Adjusted R squared is 0.6053. F statistic is 77.17 on 3 and 146 degrees of freedom. And your p-value is a really low value. So now what we're going to do is we're going to check on nesting for R. So So we're going to check on nesting for R. So M tiny becomes LM, that's a linear model, brackets Y tilde X1, and so that's data equals my data. So this is going to be a simple linear regression because you've got one dependent variable and one independent variable. And then you've got M small becomes LM, that's linear model, brackets Y becomes X1 plus x2, and data equals my data. So this is a little bit larger model because you've got one dependent variable and two independent variables. And you have M big becomes LM, that's linear model, brackets Y tilde x1 plus x2 plus x3, and data equals my data. So this is a large model because you have one dependent variable and three independent variables. And so we're going to perform an ANOVA on M tiny, M small, and M big. And it's going to say it's valid only if it's nested. So this is giving you the comparison of 1, 2, 3. So you're going to 1 is tiny, 2 is small, and 3 is big. And so you get your ANOVA for that. And so that's comparing nested models. So now, after we have done all that, what we're going to do is we are going to build a multivariate model and interpret the results. So the first thing we want to do is we want to simulate a multivariate model, and this is pretty much the same thing that, much of the same thing that we have done previously in this video. But the first thing we want to do is we want to set our seed to simulate a multivariate data set. So when you set your seed, every time you run the cell or run the program, the variables are going to be initialized to the same value. So you set.seed brackets 1, 2, 3. You can put any number you want in the brackets. N is going to be your number of samples. It's going to be 200. And then x1, x2, x3 are going to be your independent variables. So x1 is a randomly sampled normal distribution of 200 samples with a mean of 10 and a standard deviation of 2. S2 is a randomly sampled normal distribution with a 200 samples with a mean of 5 and a standard deviation of 1.5. And X3 is a randomly sampled normal distribution with 200 samples, a mean of 0, and a standard deviation of 1. And there you have predictor 1, 2, and 3. So now we're going to define the true underlying model, which is y becomes 4 plus 1.2 times x1 minus 0.7 times x2 plus 2.5 times x3 plus r norm brackets n comma st equals 3. So that's going to be randomly sampled normal distribution of 200 samples with a standard deviation of 3. So my data is going to become a data frame, and you're going to create a data frame of y, x1, x2, x3 by typing my data becomes data.frame brackets y, x1, x2, x3. So we're going to fit the multivariate regression model. So model becomes LM, that's linear model, brackets y tilde x1 plus x2 plus x3, comma, data equals my data, and then we're going to summarize the model. So call is going to be linear model, brackets, formula equals y tilde x1 plus x2 plus x3, and data equals my data. You've got your residuals of your minimum value, your first quartile, your median value, your third quartile, and your maximum value. You've got your coefficients for the intercept and x1, x2, x3, and you've got some significant codes. So your residual standard error is 3.082 on 196 degrees of freedom. Your multiple R squared is 0.5513. Your adjusted R squared is 0.5445. Your F statistic is 80.28 on 3 and 196 degrees of freedom. And your p-value is a very low value. So now what we're going to do is we're going to plot the model. So par brackets mfro equals c brackets 1 comma 3. So that's a vector that you have created. And your partial regression plot for x1 is going to be term 1 becomes LM brackets y tilde x2 plus x3, and data equals my data, and it's $ residuals. And pred1 becomes LM brackets x1 tilde x2 plus x3, and comma, data equals my data, $ residuals. And plot brackets pred1, comma, term 1. Main is the title of the plot, being partial effect of x1. xlab is your label on your x-axis, being x1 residuals. ylab is label on the y-axis, being y residuals. PCH is the size of the dot, it's 19. Color equals RGB brackets 0, 0, 1.01, 0.4. And then we're going to put a line in the plot. So we're going to say A lead line brackets LM, that's linear model, brackets term 1, real tilde, prediction 1, color equals red, and line width equals 2. So we're going to do a partial regression plot for number 2. So term 2 becomes LM brackets Y tilde X1 plus X3 data equals my data $ residuals. Pred 2 becomes LM brackets X2 tilde X2 tilde X1 plus X3 data equals my data $ residuals. And then we're going to plot brackets pred 2 comma term 2. Main is the title of the plot, being partial effect of X2. X lab equals X2 residuals. That's the label on the x-axis. Y lab, which is the label on the y-axis, is Y residuals. PCH is the size of the dot, is 19. Color equals RGB and brackets 0, 0, 1, 0.4. And then we're going to put a line in the plot. We're going to say AB line brackets LM. That's for linear model. Brackets term 2 tilde pred 2. Color equals red. Line width equals 2. So we're going to do a partial plot of X3. So term 3 becomes LM brackets Y tilde X1 plus X2 data equals my data $ residuals. Pred 3 becomes LM, that's linear model, brackets X3 tilde X1 plus X2 data equals my data $ residuals. Plot brackets pred 3 comma term 3. Main, which is your title, is partial effect of X3. X lab, which is the label on the x-axis, is X3 residuals. Y lab, which is the label on the y-axis, is Y residuals. PCH equals, and that's the size of the dot, equals 19. Color equals RGB, and RGB has to do with colors. It's a vector. Brackets 0, 0, 1, 0.4, and then we're going to put a line in the plot. So AB line brackets LM, that's linear model, term 3 tilde pred 3, color equals red, and line width equals 2. And then so what we're going to do is we're going to show the plot. So this is what we plotted. So you can see here that what we plotted is X1, X2, and X3. So X1 is a positive correlation. X2 is negative correlation. And X3 is also a positive correlation. But we're going to interpret it. So we're going to interpret the results. So X1 has a strong positive effect with a coefficient of 1.2 and a clear upward trend. X2 has a negative effect with a coefficient of negative 0.7 and a downward slope. And X3 has a strong positive effect with a coefficient of 2.5 and a steep regression line. So basically, we interpreted this correlation, and you can see the interpretation by looking at the charts. And that's it for this video. I mean, I knew it was going to be a long video. Thank you for sticking with me to the end. The next video is going to be on another statistical topic, and I certainly hope that you decide to watch it And I hope that you got something out of this video, because we did cover a lot of material concerning multiple linear regression.